it was an advance in our ability to factor large numbers, but still nobody knows if there's really a very efficient way. If the numbers get large, say 10,000 decimal digit numbers, I think no one would claim they have an algorithm to factor general numbers like that. Now how about this number? It turns out that if you have 1,031 ones, that is prime. And is that the last prime of this form? Certainly not. Certainly there must be infinitely many, but again, we don't have any tools to prove that. This looks like it might be prime. 270,343 is acting like a prime number. I mean, that's a pretty big number. You can do probabilistic tests on a number, and if it's composite, we say with probability 1/2, it says, I'm composite. And if it's not, it just won't say anything. If you do this test over and over, and it never says it's composite, then you have a feeling maybe it's prime, but that isn't a proof. Well, here's an example now of the computer kind of its full strength. In fact, I don't know if you just logged into Google yesterday, you saw a Rubik's Cube. And this is the 40th anniversary of the kind of introduction of Rubik's Cube. And one of the questions is, if you scramble up a cube, how many moves would it require with the best possible algorithm to restore it? And some mathematicians worked on this problem, and they said, well, 30 is definitely enough, and 28, maybe 26, maybe. Well, it turns out that there are a lot of possible different configurations, and the largest number of moves you ever require to restore it is 20. This is so-called God's algorithm. Never takes more than 20 moves. How do you know? Well, you just start each configuration and you check it. Well, there are only so many, right? Only how many quintillion? And this was something that actually they did at Google on a lot of servers, and just crunched it and took care of the 3 by 3 by 3. They make larger cubes now. You've probably seen the 4 by 4 by 4. And there's a beautiful 8 by 8 by 8, actually, which, now because of the 40th anniversary, they're actually mounting a traveling exhibit of Rubik's Cubes, including the world's most expensive toy, a $3 million diamond Rubik's Cube, which is traveling. So here's kind of an unexpected interaction between the ideas from computer science and mathematics. And what we have here is 14 fractions, starting with 17 over 91. And the last one is what? 55 over 1. And what you're supposed to do with these fractions is the following. You start with 2, and you repeat the following process. Namely, I'm going to go down this list and multiply by the first fraction I come to, so the product of 2 and that fraction is a whole number. Well, you see, it's going to be 15 over 2 is the first fraction you come to. So we'll start 2 times 15 over 2 is 15. Now you start with 15 and you go down the list and multiply by the first fraction, you get a whole number. Well, it turns out that in that case, it's going to be 55. So if you do that, you get 825. And you just keep this up. Each time you get a whole number, you go down the list from the beginning and multiply by the first fraction where you get a whole number. And pretty soon, you'll get to 4, which is 2 squared. Okay, just write, when you get a power of 2, write the exponent. Keep going with 4. So that's 15 over 2, 30. And eventually, not too long, you'll get to 8. Okay, that's 2 cubed. And then pretty soon, you'll get to 2 to the 5th, and somewhat later, 2 to the 7th, and so forth. And these exponents of 2 turn out to be these numbers, 2, 3, 5, 7, 11, 13, 19. Turns out these are the primes. They're all the primes. They're only the primes. So this set of 14 fractions in this algorithm generates exactly the set of prime numbers. Now this seems unlikely, doesn't it? Here I just have 14 primes. What's really going on? Well, this was one of the many nice creations of John Conway, the inventor of the game of life, although if you go to YouTube, you can hear him say he hates the game of life, actually, because people think that's the only thing he did. You say, no, he did a lot of things. He did this, for example. And what he did, he kind of embedded a Turing machine with unbounded registers, these are the exponents, and it's doing trial division, is what's being carried out. So in fact, he has a paper called Fractran, which is a takeoff on Fortran, where you can embed computations in fractions like this. So that's just, when I mentioned this result to one of the solvers of a Hilbert problem, a fellow named Andrew Gleason at Harvard, he said, well, I could see how 14 fractions might give you the first 20 or 30 primes, but how could it give you all the primes? Well, it does. Okay, now, one of the most famous right triangles, the 3, 4, 5 right triangle, the Pythagorean theorem, the sums of the squares of the legs is the square of the hypotenuse. And there are lots of solutions to having the sum of two squares being a perfect square. Here's one. And Fermat's last theorem asserted that it couldn't happen with higher powers than squares. You can't have the sum of two cubes equal a cube unless, say, y is 0. And he did prove this for fourth powers, and the apocryphal story, probably, is that in his copy of a Diophantus, a number theory book, he wrote, I have a marvelous proof of this, but the margin's are a little too small. It doesn't quite fit. But I think people feel he probably didn't have a proof. And Euler conjectured, sometime later, you couldn't even have 3 fourth powers adding up to a fourth power. And people tried pretty hard to prove that, but they couldn't prove it for one of the best reasons. Namely, it wasn't true. Now, this doesn't stop everybody, but no. Here's the smallest example. And what happened was that there were two people working on this problem, Noam Elkies and another very talented mathematician, Don Zagier, and they both developed a theory up to the point what examples should look like if they existed. But then Elkies is very good on the computer, and he started doing some computations, and that allowed him to complete the analysis and produce this example and infinitely many other examples. And so Zagier now says he now will always travel with his computer because he doesn't want to be scooped again. He should have seen it too. So here, the theory kind of pushed it up to a point, and then the computer helped complete it. So that was a good use. Now, on the other hand, Fermat's last theorem has been proved by Andrew Wiles. And here's a picture of Wiles in 1994, looking very happy. Slightly premature, actually. There was a gap that was found in the proof. But in 95, it was finally filled, and is now Sir Andrew. He's knighted, of course. And so what next? Now you've proved it. Did people really care that the sum of two nth powers couldn't be an nth power? Well, as Hilbert reminds us, once Wiles had to develop the tools to solve that problem, you can then use those tools to solve much harder problems. So we might say, okay, what next? Well, let's look at the Taniyama-Shimura-Weil conjecture on this space. No, we're definitely not going to look at that in this talk. Anyway, but it allows you to kind of push ahead. Okay, good. Now, there's an interesting related conjecture of a fellow named Andrew Beale. And what does it say? Well, it says that if you have, x to the a plus y to the b equals z to the c, but now the exponents could be different, but they have to be at least 3, and you don't have any zeros, then the only way that can happen, they must have a common factor. So for example, here's 3 cubed plus 6 cubed is 3 to the 5th. Or here's a bigger one that has big powers of 7, and so forth. It's easy to produce these. And if this were true, it implies Fermat. I asked Wiles about this. He said, no, it's kind of hopeless. In fact, Beale has now raised the prize up to $1 million. We'll talk a little bit more about $1 million prizes. But who is Andrew Beale? Well, Andrew Beale owns the largest private bank in Texas, has a satellite launching company, he's a multi-billionaire, and kind of an amateur mathematician as well. And he just thought that this seemed to be true. And I think he had a lot of people checking for counterexamples. They couldn't find it. There's an interesting book called The Banker, the Professor, or The Professor, the Banker, and the Suicide King. And Andy Beale is also a very good Texas Hold'em card player. And he thought he would like to go to Las Vegas and challenge the best professional card players with the advantage that he thought he would have in the following sense. Namely, if you were to go and play against the best Texas Hold'em players in Las Vegas, the advantage they have over you, first of all, they're good players. Second of all, if the pot has $20,000 or $30,000, it means something to you. And you can't bluff in a convincing way. You can't play optimally because the money is important. For the players, they're used to that. It's probably not their money. He thought he would turn the tables and have the stakes so large that they would get nervous. And it worked for a while. But then they kind of ganged up on him, I heard, and he lost maybe $30 million. He said it was worth it. It was worth it. So anyway, it's a nice read if you want to read about Andy Beale. Well, okay, in mathematics, one of the most fundamental structures are arithmetic progressions. These are just sets of equally spaced numbers like 3, 5, 7, 9, or 399, 409, and so forth. In fact, this last set is, they're all prime numbers. And an old question was whether or not you can have arithmetic progressions of just prime numbers that are as long as you like. Could you have an arithmetic progression of length 100 and they're just prime numbers? Well, people looked at that for quite a while until fairly recently. There's a nice result that kind of led to a lot of things by Ben Green and Terry Tao. In fact, they're both just up the road, an hour away at UCLA this week, that there are arbitrarily long progressions of primes. And in fact, they show there's a k-term progression. They're all less than this somewhat large number. In fact, that's certainly not the best possible. I think the estimates are much better now. But a related problem, it seems kind of untouchable at present, show that you can find arbitrarily long arithmetic progressions of consecutive primes. That is, not just that they're primes, but there's no other primes in between. These are consecutive primes. The current record is 10. And these are the numbers p plus multiples of 210. And what is p? P is that number. It doesn't fit on one line. If you take that number and add multiples of 210, you'll get 10 consecutive primes. And the people who did this feel they'll never be able to find 11 by that technique. And we don't know. Now for something completely different, combinatorics. So what is a graph? Well, a graph consists of vertices, V, points, and edges. These are just pairs of vertices. And these are very useful in modeling relationships. You have objects, and you have relationships between the objects, and you put an edge. So if this is one of these pairs, one of these edges, I'll just write X, kind of wiggle Y. So for example, you can draw pictures. Here's a 5 cycle, 5 points in connected cycle. Here's the complete graph on 5 points. 5 points on all possible edges, okay. And here's a couple other graphs, the Moser graph, the Peters graph, and in combinatorics people look at a lot of graphs. In fact, nowadays, one of the big topics, these social network graphs. So maybe your vertices in your graph are websites, and if one links to another, you put an edge. Well, there's hundreds of millions of these things. But here's the Peterson graph, and when you write a graph, it doesn't matter how you draw it, it's just what's connected to what. If you can relabel the vertices and preserve the adjacencies, it's the same graph. So here are pictures that it's actually the same graph. It just looks a little different. But there is a labeling so that exactly edges and non-edges are preserved. In fact, the whole question, if I give you two representations of two graphs, are they really the same graph, is not. There's no efficient algorithm known for solving that right now, but we'll get into that in a little bit. Well, okay, you'll say something is an R coloring of a graph. Just means each vertex, I'll give you one of R colors, but make sure that adjacent vertices have different colors. That's the only requirement. You're going to put colors, and you want to make sure that adjacent ones have different colors. And of course, one thing is to color every vertex a different color, but you'd like to minimize the number of colors. And the chromatic number of your graph is the smallest number of colors so that you can color your graph legally. So, and this idea came up, we'll see in a minute. So here is, for example, the complete graph on 5 points, and I claimed the chromatic number is 3. Here's a 3 coloring, and adjacent ones have different colors, and you can't do it with 2. So it takes 3, and you can do it in 3, whereas this so-called Moser graph takes 4. You can't do it in 3 colors, so it takes 4. Now, what about this graph? I have no idea. I don't know what it is. It's probably, well, I don't know, something. The chromatic numbers at most 2 if it has no odd cycle, like a 5 cycle. What about 3? Well, this is one of these, and we'll see in a minute, computationally intractable problems. There's no known algorithm that terminates in a reasonable amount of time. You input a graph and you say, can you use 3 colors? Can't tell, can't tell. A graph is said to be planar now if you can draw it in the plane so that the edges don't cross. So, for example, here is this Moser's graph, but if I stretch out the bottom, I could draw it that way. Of course, you don't have to do straight lines, I just put straight lines. This is a planar graph, and whereas this graph right here, this Peterson graph, is not a planar graph. No matter how you draw it, you're always going to have edges that cross. And the 4-color conjecture from more than 150 years ago, if a graph is planar, it takes at most 4 colors. And this came up in connection with cartographers who were mapping the counties in England. And you want adjacent counties to have different colors so you can kind of distinguish. And they noticed that 4 colors was always enough. And the 4-color theorem, proved in '76 by Appel and Haken, said the 4-color conjecture is true. They needed many nice ideas to reduce it down to a finite problem, plus 1,500 hours on the largest mainframe they could have at that time. And people sometimes forget now that actually this paper, in '76, there were 2 papers that came out to prove it. And the second paper had a 3rd author, Koch. He was the programmer. It couldn't have completed the program and the proof without that. People have tried pretty hard to see, well, is there a human readable proof? There were billions of computations in this, and recent progress, Robertson, Seymour, and others, is still true. It took 3.5 hours on a Spark 20, billions of computations. Will there ever be a proof that a human can read? It's not clear. It's not clear. In fact, this is a special case of Hadwiger's conjecture. What is that? Well, one definition, and then we'll zoom away here. You'll say that a graph H is a minor of another graph. So I'll say G contains H as a minor. If you can obtain H from G by deleting vertices and edges and contracting edges. So for example, here is our Moser graph. If I contract this edge, it kind of swallowed up. Now I have these extra edges. I can delete those. And now I have extra vertices, contract that, and now I get a K4. So K4 is a minor of M, okay? And the Hadwiger conjecture says that if your chromatic number is at least K, then it must contain the complete graph on K vertices as a minor. And it turns out that H5 is equivalent to the four-color theorem. That's the four-color theorem. H6 was proved by Robertson Seymour. It's true, but then they're stuck. That's it, stuck. I would hope to live long enough to see HK in general, but you know, Seymour is stuck, so that's not a good sign, right? Here's a picture of Erdős and Hawken. Maybe Erdős is actually explaining a book proof to Hawken. Hawken feels, in fact, that the four-color theorem is true because many billion things happen to be true individually. There's no global, nice algebraic proof, but that's hard to prove that. Well, here's kind of a scary trend now between computers and mathematics. So in a graph, you can define the distance between two vertices, x and y. This d is just the number of edges in a shortest path. So for example, here's our Peterson graph. Here's u and v, and the distance is 2 because there's just a path of length 2, okay? And you could average, you could add up all the distances between all pairs of vertices, and there's n squared pairs of vertices, and that's kind of the average distance. So for this graph, the average distance, 1.5. Just add up all the distances, okay? Now, another thing you can do for a graph is the independence number. That's just the largest set, the size of the largest set, so that there's no edge between any two of them. So for example, here I claim it's 4. Here are 4 vertices, and there's no edges between any two of them. And you'd think that if the independence number is large, then the average distance should be large. They should be related. And there was a nice conjecture for all connected graphs. The independence number is at least as large as the average degree. This was a complicated proof, proved by Fan Chung, one of my favorite co-authors. And the interesting thing here, though, is that graffiti is actually a computer program created by an AI researcher at Houston, Simeon Feitlowitz, who has produced some 6,000 conjectures in graph theory and now geometry. And in fact, he says one of the most difficult things is to decide whether a conjecture is interesting or not. And the computers are not so good at proving conjectures, but they seem to be very good at generating these things, and there's just a few thousand of these things that look kind of interesting, and just nobody's, you know. There was a group that spent a summer, I think at IBM, to try to look at a few hundred of these to see, and it turns out that about half of them were not true, and a few of them were kind of trivial, and the rest, they just couldn't decide, you know, have to. So, we ever catch up? Well, computers are, you know, we have to teach a computer to settle the conjectures, not just to make the conjectures. Well, here's a little complexity theory. So P in computer science denotes the set of problems that you can find the solution in polynomial time. And we'll see some of these problems. NP seems to be a larger set of problems. If somebody alleges there's a solution, at least you can check it in polynomial time. So, for example, the hardest problems in NP are called the NP complete problems. And it turns out every problem, every NP complete problem is a special case of every other NP complete problem. And here's kind of a little landscape. So linear programming, sorting a list of n objects, find the convex hull, and the NP complete problem is a chromatic number equal to 3, or traveling salesman problem, 1,000 of these problems. And this was kind of a no man's land until pretty recently. 2 undergraduates and an Indian professor in India showed there is a polynomial time algorithm to testing that a number is prime. So you can actually test whether the number is prime, but to factor it now, that seems to be up in the air. So here's an example of bin packing, okay? So here is 100 10-digit numbers, and you imagine these are weights, and you're trying to pack these 100 weights into 10 bins, and each bin has capacity 50 billion. Can you partition these 100 weights into 10 sets where each set has size at most 50 billion. Well, it's going to be close because the sum of all 100 is 500. So it's just going to barely fit. And you recognize these numbers? Well, no one knows. Here, if I put a 3 there, 3.141592657 digits of pi. Well, not all 100 numbers are digits of pi. This is my Social Security number. I put it down there just so in case you forget it. Well, I better get that off the list. Okay, good. So, as I said, all of the problems that are NP complete, each one is a special case of any of the other ones. So if you ever found a good algorithm for doing one of them, good means if you put the problem in and it takes polynomial, there are polynomial many steps to settle whether the problem is, whether you can find the solution in terms of the size of the problem. So, big question, are these problems for which you can check the solution in polynomial time, can you actually always find the solution? Is P equal to NP? And this is the #1 problem on a recent list of million-dollar problems. And most experts think the answer is no, that these NP complete problems are really harder. There's, in general, no polynomial time algorithm to settle them. In connection, in the year 2000, the Clay Mathematics Institute put a list of 7 $1 million problems. And at the top of this list is P versus NP. So even though it kind of comes out of computer science, the mathematician says, yeah, this is a key problem. You'll notice another problem on this list, the Poincare conjecture, you may have heard recently. And this was a problem which was, in fact, solved by Gregory Perelman, who's currently living in Moscow, last I heard. And, well, does he get his million? Well, he was offered it, but he didn't want it. He says, I don't want it. You can have it. So, well, it's his choice, right? So now there are 6 Millennium Prize problems left. Although you have the Andy Beal conjecture if you want. Well, how about a little geometry? Okay, here's a knotted double torus, and you'd like to transform this picture to the, imagine this is some strange bicycle tube. It's flexible, it's full of air, and you're trying to stretch it and warp it in such a way, but you can't tear it to get this figure. Well, can you do it? Well, as a human, you'd say, well, of course you can't do it. But a machine with the right algorithm would say, of course you can do it. Yes, yes. And how would you do it? Well, you could start with this. You could kind of stretch it a little bit, kind of warp it, if you can mentally see how that would happen. And then kind of shrink the neck and expand it out. And then start peeling this piece off. And it kind of looks like that. Well, okay, I'll show you. Here's a little. Let's do it again here. Let's see. Bonk. Okay. Bonk. Yeah. Well, okay. So I don't know if that's convincing, but so computers are not hindered by this intuition. They said, well, of course you can do it. In fact, there's a whole series of these things that look very strange. Now a little more geometry here. Square packing. And here I've had to change my mind. So you look at squares of side lengths, infinitely many squares, side lengths 1, 1/2, 1/3, 1/4, and 1/5, and so forth, and you want to pack them into a rectangle of size 1 by pi squared over 6. Now why pi squared over 6? Well, the sum of all the areas of these is the sum of the reciprocals of the squares, and Euler showed that was pi squared over 6. So here's a start. So here's the 1 by 1, and the 1/2 by 1/2, and a 1/3 by 1/3, and a 6, and so forth. And I just didn't think you could do it. I think it's going to get really jagged over there. But there's a computer scientist, Clive Tooth, who got the first 100,000 in. In fact, the first 100,000. So I'm now starting to change my mind. maybe you can do it. He even has an algorithm of what he's doing. He just can't prove you can continue. So I don't know if you can go all the way. I offer a modest, in the tradition of politics, a modest 250. Prove you can go all the way or prove you can't. I don't know. Now, here's something that goes back kind of quite far. The Rhine Papyrus and Egyptian fractions. Turns out that the Egyptians like to write fractions as sums of distinct positive integers. So you want, say, 4/7 is a half plus 14ths. So you want these numerators to be all 1, and the denominators should be distinct integers. And Fibonacci proved you can always do it using a greedy algorithm. Namely, just subtract the largest one you haven't used yet, and pretty soon the numerators start going down, and so it has to terminate. In fact, I once asked André Weil, celebrated mathematician, why he thought the Egyptians used represented fractions like this. And he was quite an expert in history. He thought about it for a minute. He said, it's easy to explain. I said, yes, what is it? They took a wrong turn. That was, it was a mistake. Shouldn't have done it. Well, anyway, they did. So now, suppose all the denominators are odd numbers, and you have an odd number, and it's known you can always represent an odd fraction, a over 2n plus 1, as a sum of distinct odd numbers. Because the greedy algorithm always work? Well, here's some examples. Okay, so here's a program. So say we take 4/95 and we try to do it. Boom, okay? Or, well, whatever you want. Say 4/99. Well, that was easy. Okay, about 4/991. How about that? Okay, 4 steps. Well, okay, how about 5/139? Boom. Took 19 steps, and I guess the last denominator had 562,000 digits. Okay, well, can you always do it? Those are the examples. For example, 5 over this 1444613 takes 37 steps, and the largest denominator has 384 billion decimal digits. And computation is trying to tell us something. Can you? And there are many fractions. It just goes, and then it doesn't seem to stop because each step, the denominators definitely kind of typically double in size, kind of square, and you're just beyond computation. You know, if you require they have square denominators, then long ago I showed that you take any number that has a chance in these 2 intervals here, you can always write it as a sum, any rational, as a sum of distinct perfect squares. Does a greedy algorithm terminate? $25. In fact, hardly ever terminates. I don't know. But anyway. Here's a recurrence that came up in looking at some sorting algorithms where computation doesn't seem to be very useful at all. You define xn plus 1 in terms of xn, namely xn minus 1 over xn, start at 2. So if 2, then the next one is what? 2 minus a half, that's 3 halves. And then the next one is 5/6. And you keep going, minus 11 over 30 and so forth, and it just goes for a while. And if you kind of plot this, you see you get these points here, and because you're subtracting the reciprocals, you're just chipping away. It comes down and down until at the 24th step, you get number 0.04. And now xn minus 1 over xn is a big negative thing because you're divided by that tiny thing. And so boom, x25 is minus 24. But now you just chip away again, and it's slowly. And the question is this unbounded if you go, or does it just stay bounded? We haven't a clue. Here, computation isn't helpful at all. Any small round-off error gets magnified so much, you just you can't tell anything. So doesn't seem the computation is helpful at all there. Here's a recurrence that came up in looking at a sorting algorithm. Again, you define xn plus 1 in terms of xn, namely you multiply xn by 1 more than xn, double it, take the square root, round it down, start at 1. And if you do that, you get these values here, 4, 5, 6, and 7, and so forth. And okay, well, what are these numbers down here? Well, it turns out if you look at whether they're even or odd and look at every other one, you get the 1, 0, 1, 1, odd, even, odd. You look at this number, and the question came up, is that periodic? Does it have infinitely many zeros and ones? What could you say about it? Well, they came to me at Bell Labs, and I looked at it, and surprisingly, this looked kind of familiar. And why was it familiar? Well, if you put a decimal point right here, this is the square root of 2 in binary. So this number actually gives you this square root of 2 in binary. And in fact, let's back that up there. So that was soup, right. Now, how you recognize numbers. So you could do the same thing with 3 and look at it mod 3 as you get zeros, ones, and 2 and so forth. And you look at this, and that doesn't look like it's anything. And there are now programs which, if you look at the decimal expansion or some expansion, it'll try to guess what the real number is. But there are an awful lot of real numbers, so it's usually not very good. So the whole question, even recognizing 0, is hard. Well, the last topic, I'm going to look at some large numbers. You think, well, computer's really good computing large numbers. Here's a large number. Well, you can write any number as the sum of distinct powers of 2. Here's 41 is 2 to the 5th plus 2 cubed plus 1. And in fact, what we're going to do is not just stop with 5, 3, and 1, but you're going to represent all the exponents as sums of distinct powers of 2. So you call this the super base 2 expansion of 41. So you write a sum of powers of 2, but every exponent sum of powers is 2 and so forth. And you're going to do an algorithm. You're going to replace each 2 by 3, subtract 1, and make sure that the number is in super base 3. So in this case, you would replace each 2 by a 3, and then subtract 1, you get that number, which turns out to be, 22, well, I don't know, quadrillion, maybe more. Okay, now the next step, replace each 3 by a 4, subtract 1, and make sure it's in super base 4. Well, if you replace each 3 by a 4, subtract 1, well, that's not even a base 4 expansion. You can't have minus 1. So it's a little bit like you have 1 million and subtract 1. Well, you've got to go 999,999. So the base 4 expansion of this is actually this same power of 4 plus 3 times this, plus 3 times this. So these 3's are coefficients, and that's the next step. And that number is equal to that. And you can see the next step, replace, in general, the super base b by b plus 1, subtract 1, and then super base b plus 1. So for example, here, that's what you get with 5. And the numbers are getting bigger, right? Pretty close, because I'm replacing the super base by, well, an amazing result is that, oh yes, that 6 is not correct, right? It couldn't end at a 6, right? There's one more digit there. That's a 7. That's it. Actually, these digits could be completely bogus. How could you check? But trust me. Okay, good. So the fact is, if you keep repeating this process, you eventually get to 0. Now, it doesn't look very promising at the beginning. It's kind of taking off kind of big. This is a consequence of Goodstein's theorem that says for every integer n, you start with the super base 2, and you go through this process. Eventually, you get to 0. And this is an example, a kind of a weak example of what's called Gödel's incompleteness theorem. Here's a theorem that lives in what's called piano arithmetic, which is kind of fragment of mathematics that we work in. And yet you can't prove it there. You have to go outside the system. And if g of n denotes the number of steps to get to 0, given that you start with n, then if you start with 2, you get to right away, or 3, it takes 5 steps. Okay, what about 4? Well, it starts 2 squared, goes to 3 cubed minus 1, which is here, which goes to here, which goes to here. You might say, well, I'll put it on my computer and let it run, and then come back after lunch and see how many steps it took. Well, g of 4 turns out to be this number, which is greater than 10 to the 100,000th power. So this algorithm takes a long time to complete. You wouldn't want to wait for it, right? And no one's ever computed G6 for a modest 25. Of course, you hand me a big sheaf of papers and say, okay, here it is. I'd have to check, I guess. I had this offer for 5, but I had a very good grad student who did 5. So 6, I don't know. Well, the most wanted problem on the list, the Riemann hypothesis, which is what? Well, you have this Riemann zeta function. It's the sum of the reciprocals raised to an s power, but s could be a complex number now. Remember, we saw that zeta of 2 was square root over 6, or zeta of 2 plus I is something here. Zeta of 1/2 plus this number is 0. And these zeros are of great interest to people in number theory. And if you knew about the zeros, you know a lot about properties of prime numbers. And here is a picture of the first few zeros of the zeta function, 1/2 plus I times tau, and here was our 14, and these are the zetas, the non-zero zetas. And the hypothesis, the Riemann hypothesis, says that all the interesting zeros have the real part 1/2. And it's true for the first 10 trillion, they checked it. In fact, here's a few easier problems. The last problem, another four-color conjecture. It's kind of Erdős loved this problem, it wasn't his. That if you color each point in the plane with one of 4 colors, must you always find a pair whose distance 1 with the same color. So again, I'll give you your crayons, and each point gets one of 4 colors. Can you avoid having 2 points, distance 1, the same color? If you had 7 colors, you can do it. And it's not true if you only had 3 colors. And you know, it's been open since 1950. And okay, the last problem I'll mention, h of n. This is called a harmonic number. You just add up the reciprocals of the first k integers. So it's known it grows kind of like log n, the harmonic number. Here's another function. You just take for each integer n, add up all the divisors. So for example, for 6, the divisors are 1, 2, 3, and 6. So sum of the divisors of 6 is 12. And harmless question, is it true for every number n, if you add up the sum of the divisors, it's at most h of n plus e to the h of n to the natural log of h of n. Is that true or false? Well, I don't know, but it's worth $1 million. Really? Why? It is equivalent to the Riemann hypothesis. If you found one n for which this is violated, you have infinitely many zeros off the critical line. And so this again reflects Hilbert's remark, you often can't tell. Here's a harmless looking problem. Well, it's the Riemann hypothesis in disguise. So it's true for n less than 10 to the 100th, for example, because you know a lot about the zeros. But Lisko computed the 10 to the 22nd zero of the zeta function and his billion neighbors. And his conclusion was, if it's true, it's just barely true. It almost fails, but didn't quite fail. And my former colleague, Dick Hamming, said, what's the purpose of computing? It's not the numbers, it's the insight. You want to get insight. But someone remarked that maybe there's another twist on that. Namely, the purpose of computing is not yet in sight. So computers are just beginning to reach their stride, especially if you talk to people like Doron Zeilberger. If you ever want an interesting website, check out his website, you know. But so, will we ever know whether the Riemann hypothesis is true? Well, I subscribe to Hilbert's philosophy. We must know, we will know. Of course, he didn't say that. I mean, he said, it's said that he said, Wir müssen wissen, wir werden wissen. That's what he said. Now, did he really say that? Is that just a story? Well, in fact, yes, he did say it. And
wir dürfen nicht denen glauben, die heute mit philosophischer Miene und überlegenem Tone den Kulturuntergang prophezeien und sich in den Ignorabimus gefallen. Für uns gibt es kein Ignorabimus und meiner Meinung nach auch für die Naturwissenschaft überhaupt nicht. Statt des törichten Ignorabimus heiße im Gegenteil unsere Losung, wir müssen wissen, wir werden wissen.
He said it, didn't he? This is from 1930 on YouTube. So I personally believe that, you know, the Riemann hypothesis, we must know, we will know. Of course, the we, that's not clear. You know, may take a little bit longer, but anyway, I'd like to wind up with the interesting things people are doing. As a juggler, I like kind of the, you know, you might say, oh, here's the baseball. It's baseball season, right? In fact, of course, you have the Cardinals, and they have the ordinals. If you're in the new math, maybe that's... So you might say, you know, what's the use? There's no Nobel Prize in mathematics, which is true, but not for the reason you may think. Nobel didn't have a wife, so no, it's for the useful sciences, you see, so math, astronomy. But, you know, there is the Abel Prize. In fact, there's Simredi, who got it a couple of years ago, and then more recently, Deline, and then just very recently, Sinai, all in New Jersey. So New Jersey's doing pretty well. And back to our research activity here. Well, okay, good, logic. So, thanks for showing up, and hope I've given you some food for thought and some ways to earn some maybe not so easy money. So, thanks again.
Are there any human-readable proofs of the four-color conjecture for maps that would cover sort of most of the maps we'd reasonably expect to have, like, you know, those with no more than 100 vertices or something?
I think if you look, okay, so the question is, are there any kind of human-readable partial proofs of the four-color theorem, or at least, I think you can read, I think in the Seymour, the Robertson-Seymour, at least they explain the philosophy of what they're trying to do, and then you get down to computations. There's a bunch of mathematicians trying to supply formal proofs. That is, prove that the proof is really a proof, and put in all the details. And I think the four-color theorem has actually been verified that that really is a proof. Because you might say, well, how do you know the computer program at some point didn't make a mistake, or a cosmic ray came in just at a crucial, but you know, there is a point of view that in some sense it might be that the theorems that we as mathematicians can actually write proofs down for are very special, very singular. And most theorems are like, say, classification of finite simple groups. That's a problem. You'd like to classify all the finite simple groups, and you can state the problem on a page, but originally it took about 15,000 pages to prove, and maybe it'll get it down to 3,000 or 2,000. Will there ever be a 5-page proof? Probably not. Well, I don't know. And there certainly are kind of subfields within mathematics where you can prove that there are true statements on n symbols whose shortest proof grows doubly exponentially. So it may be that the things that we can actually write proofs are kind of pretty special, and they're the interesting ones. But it's like the integers. Maybe all the really good stuff happens way out there, you know. I mean, there are a few people who believe the Riemann hypothesis is not true. There are zeros that are off the critical line, but they're just so far out that you won't find them. But, you know, hard to know. Yeah.
Any other questions? Okay, let's thank Ron again. Well, I thank the organizers for inviting me to give a talk at this conference. I was not an obvious choice. I have never been to Uzbekistan, but in some sense we all come from the same school. So, and I'm a local guy. San Diego is in 1.5 hours from here. This is a joint work with Consuelo Martinez, and we always consider algebras over an algebraically closed field of zero characteristic. Arnold used to say that you can always recognize an algebraist. They always start their talk with, let F be an algebraically closed field of zero characteristic, instead of saying a field of complex numbers. Well, the famous Virasoro algebra is the algebra of derivations of Laurent polynomials. It has, can I show? Oh yes, it has this basis, and it has a very interesting central extension. Well, this algebra was first mentioned by Richard Bloch. Then it was studied by Gelfand and Bernstein. And finally, physicist Virasoro wrote something about it. So it became known as Virasoro algebra. Now I will talk about superalgebras. Superalgebras were introduced in 50s in algebraic topology, I guess, and modest mathematicians call them graded algebras. Later, connections with supersymmetry were found, and so they became known as superalgebras. It does not mean that they are superior to other algebras. It just means connections to supersymmetry. So since Virasoro algebra turned out to be so useful, and it was involved in so many meaningful physical models, the idea was maybe we can find some nice super extension of it, and it also will be used in physical models. So what are Lie superalgebras? A superalgebra in general is just an algebra which is graded by a cyclic group of order 2. And there is a rule in that if two elements in an identity change places, please don't forget to multiply by this -1 to the power to the product of parity. It means that if both elements are odd, that is, they lie here, then it is -1. Otherwise, just you may ignore it. And this is super Jacobi identity. Now, some examples of superalgebras. We could consider a graded matrix algebra of size m plus n, block graded. And then block diagonal matrices are declared even, and off diagonal matrices are declared odd. And the operation is this. It's a typical example. A and B were changed places, so I had to multiply by this coefficient. In general, a Lie superalgebra is not a Lie algebra. It is something different. L0, the even part, is a Lie algebra. This is a module over this Lie algebra. And then there is a pairing, a product of two odd elements, which is an even element. Another example, Grassmann algebra. Well, this is the algebra presented by these generators, Grassmann variables, and these are defining relations. So they all anti-commute, and their squares are equal to 0. Then a basis consists of ordered products, and if the length of that product is even, we say that this is an even element. Otherwise, it is an odd element. So it is a sum of an even space plus an odd space. But it is an associative superalgebra. It's not Lie. We can view it. We can put together even variable and odd variable So this is a tensor product of the polynomial algebra and Grassmann algebra. And we can consider derivations and super derivations of this super polynomial algebra. I may get tired of repeating super each time, so I can refer to it as polynomial algebra, derivations. Fortunately, the concept of derivation was introduced in the previous talk of Professor Ayupov, so he saved me some time. And all derivations look like this, including super derivations. You know, you can treat these Grassmann variables as ordinary variables, take partial derivations. Now, in 70s, this activity started. Physicists started to look for super extensions of the Virasoro algebra. The first such super extensions were found by Nevier, Schwarz, and Ramon. And then more serious SU2, so-called old terminology was introduced by physicists. So I don't know even what stands behind it. SU2 superconformal algebras introduced by Seiberg, then SON, a group of Italian physicists, forgot the names. Well, so these were all super algebras containing Virasoro in the even part and somewhat nice. In 88, Katz and van der Leur, they linked these works to the old works of Cartan. They kind of explained these superconformal algebras. Well, the theory of Cartan studied infinite dimensional algebras that arise in differential geometry at the beginning of 20th century, and he introduced 4 big families of infinite dimensional algebras of Cartan type. You may consider all polynomials and their derivations. It is a simple Lie algebra, infinite dimensional, of course. You may consider those of them that have zero divergence. And then there are another subalgebras, Hamiltonian and contact. I won't even give definitions. They keep certain forms invariant. Now you can do the same in the super case. Consider all super derivations. This is a super algebra. Even derivations form an even part, odd derivations, odd part. It contains Virasoro. Then you can consider those of them that have zero divergence, even even deform them a little bit, so they would depend on a parameter. And then Katz and van der Leur noticed that these SU2 superconformal algebras are just these algebras when n is equal to 2. So they come from the old Cartan theory. Finally, Hamiltonian algebras don't appear here because in Hamiltonian algebras there should be an even number of even variables, and here we have only one. So they don't appear, but contact algebras do appear. One can consider this bracket on all these polynomials. And this bracket is strange. It is not a Poisson bracket. No, a Poisson bracket defines a Lie algebra, and if you fix one variable, then it becomes a derivation with respect to the second variable. This is not the case. This bracket defines a Lie algebra, but instead of Leibniz identity, if you fix one variable, you get a somewhat more complicated identity of degree 3. Leibniz identity is of degree 2. And this is called contact bracket. So if you take this contact bracket, it defines a Lie superalgebra, and you get another super extension of the Virasoro, and these were exactly those SON superconformal algebras. When n is equal to 2, K2 is Navier-Schwarz superconformal algebra. One can study for which parameters these superalgebras are simple, when they are isomorphic. It has all been studied. The natural question is which of them have interest in central extensions, as Virasoro does. Very few of them for small parameters. It was done by Katz and van der Leur. And that brings back the theorem of Olivier Mathieu, which he published, which appeared in 92. The story starts earlier. The story started in Moscow in 67. Victor Katz decided to study these Lie algebras graded by integers. Graded means that if you multiply two homogeneous components, their degrees just add. And he wanted to study infinite-dimensional objects, but as always, if you want to study something big and infinite-dimensional, it makes sense first to look at the small cases. So infinite-dimensional, but say growing not too fast, say polynomially. So there is an upper bound for dimensions of homogeneous components, which is a polynomial. If you want a classification, then you have to ask about graded simple objects. Graded simple means that they may contain ideals, but this ideal should not be graded. Graded simple means that this algebra does not contain proper graded ideals. And he found the following examples. Well, that was all in 60s. If you take a finite dimensional simple Lie algebra, a very well-known object, and then Laurent polynomials over it, it's a graded algebra by degrees of t. Dimensions of all components are the same. So they grow as, well, they don't grow, they're constant. And that's how Katz-Moody algebras were introduced. These are affine Katz-Moody algebras. Well, they also have some very interesting central extensions. This is one example. Another example were algebras of Cartan type and the Virasoro algebra. A very interesting classification, except that Katz could prove it only under one technical assumption, which ruled out the Virasoro. And he conjectured that if you drop the technical assumption, the only new example will be the Virasoro, which was proved by Mathieu in 92. A very complicated proof. I don't know anybody, except the author maybe, who read it completely. Now, since not we, but Katz and van der Leur came to the conclusion that superconformal algebras are algebras of Cartan type, but in the super case, and so they started the search of the same problem of Z-graded Lie superalgebras which grow polynomially and say graded simple and contain Virasoro in the even part. These are superconformal algebras. And they conjectured that the analog of Mathieu theorem holds for superalgebras. However, in 96, independently, Chen Katz and Grossman, Leites, Shepachkina, I'm very proud that at most conferences I'm the only person who can pronounce that name. Discovered a new superconformal algebra, which Cheng and Katz called CK6. CK stands for, not for Calvin Klein. And Grossman, Leites, Shepachkina did something remarkable. This is a good story for students. I don't see many students here, but they published their paper in Vietnamese mathematical journal. Nobody noticed it. and put it on archive in the section of high energy physics. As a result, nobody referred to that paper for several years. So it's a good lesson to students publishing papers in journals which are read. And if you put it on archive, think where you put it. So who are possible readers? Now, so this name CK state. Now, Cheng and Katz, Grossman, Leiter, Shepachkina practically found that algebra inside K6. Cheng and Katz gave multiplication table. Later, several more realizations were found in our joint paper with Martinez. We realized it as 8 by 8 matrices over Weil algebra. Well, now the classification conjecture has been modified. All the above plus CK6. And there are good reasons to believe that in this form it is correct, though the conjecture is still open. In 2001, in a joint paper with Katz and Martinez, we did it for Jordan case. Well, for those Lie superalgebras that come from Jordan superalgebras, and CK6 does. And the conjecture was confirmed for that case. Now, the conjecture is still open, but a different point of view emerged. Again, with the under the influence of physicists. You see, when I look, the subject of this conference is analysis and mathematical physics. I had to think, where can I come close to the subject? So there is a different point of view. You know, if you remember these superalgebras of derivations, they can be, all elements of these superalgebras can be arranged in strings by powers of t. For example, this is a typical derivation, and let us change powers of t. And the role of this variable z is, oh well, this is like a generating function. It doesn't have any role. It's just a nice way to write the string of coefficients. And such things are called formal distributions, or physicists call them fields. Laurent series are infinite in one direction, and these are infinite in both directions. Such things first appeared in analysis, in theory of generalized functions as introduced by Sobolev, and later developed a theory of distributions by Schwarz. If you consider Fourier expansion of a generalized function, it is infinite in both directions. And what I will say later was somewhat known within these theories. There is a very important axioms for these fields which they may either satisfy or not. A very important property, the so-called locality axiom. Given two formal distributions, we say that they are mutually local if this equality holds. You see, I had to change the name of the variable. Because if you have two series which are infinite in both directions, you cannot multiply them. You will get nonsense. The coefficients will be infinite sums. But if you change the name of one variable, it makes sense. That's what we did. Now, this is equivalent to, once you have any algebra and you choose a basis, you can talk about structural constants. This language is nearly forgotten now, but when people started to work with algebras at the beginning of the 20th century, that was a predominant language. You take two basic elements, you multiply them, you expand it as a linear combination of other basic elements, and you got coefficients, structural constants. Now, locality axiom is equivalent to structural constant of these homogeneous components being polynomial functions. For those who studied history of algebra, history of mathematics, after the theorems of Wedderburn, the point of view started to change, and people started to forget what are structural constants. Okay, let us look at the Virasoro algebra. That is the multiplication. Structural constants are polynomials. That's why locality axiom holds for Virasoro algebra. Now, since we cannot multiply two series which are infinite in both directions, this impossible multiplication was replaced by a countable family of partial possible multiplications. And that also goes from Sobolev and Schwarz. These are partial, positive, oh well, it is between pages. At the end, well, I don't know, what can, maybe I can move it down a bit. No. Well, this countable system of coefficients and, well, some general definition. Let L be a Lie superalgebra. This is a space of all formal distributions. C is a subspace. And we impose some axioms. Suppose that for any two formal distributions from this subspace, they are mutually local. You have to change the name of one variable, multiply, and then when you multiply some, and then multiply by the power of a difference and get 0. It's some polynomiality condition. Another condition is that this subspace is closed with respect to all partial operations. And then what can you do with these formal distributions? You can differentiate them with respect to z. So that's another condition, that the space is closed with respect to this formal, the derivation. Then it is called a conformal superalgebra. Strange definition. In principle, this stuff has a reputation of being unlecturable. One of the founders of this area gave a talk at Gelfand seminar. And Gelfand told him, you know, I'm 80 years old. At that time he was 80. I have huge experience. I don't understand your definition. Which means that something is wrong with the definition. So in case you didn't understand this definition, you are in a good company. But the star moment of this conformal or very close vertex operator algebras came in 80s. It was a very dramatic story. You know, Ron Graham already mentioned the classification of finite simple groups. A huge project. There are series and there are sporadic groups. There is a biggest sporadic group, the so-called monster. John Mackay was looking at some numerology and found that the smallest faithful representation of that monster, the size of matrices by which it can be represented, it's a 6-digit number. Differs only by 1, by some coefficient of a modular function. Since these are 6-digit numbers, it cannot be a coincidence. And then Conway, who was already mentioned in that talk, Norton, Thompson, formulated a conjecture that the monster has a graded representation, graded traces are modular functions. All modular functions can appear in this way. It became known as the moonshine conjecture. For those of you who know the English meaning of the word moonshine, I will say it in Russian. Samagon. Well, we can understand the attitude to this conjecture. One famous mathematician made a bet for a box of cognac that this conjecture won't be settled in the 20th century. The funny thing that by the time the conjecture was made, the examples of these representations already existed in the literature, but in the literature on two-dimensional conformal field theory. So one of these conformal algebras has a very interesting group of orthomorphisms, the monster. Okay, now there is the way to construct these conformal algebras. If you have pairwise mutually local formal distributions, then, well, they generate a conformal algebra. That's a way to construct them. Some examples. If G is a Lie conformal, well, any Lie algebra. Stopped working. Any Lie algebra, and we consider Laurent polynomials, then you can write the coefficients in strings by powers of t, and that's a conformal. All these formal distributions are pairwise mutually local. The Virasoro algebra that I already mentioned, algebras of Cartan type, you see that I mentioned the same examples as before. Now, so the idea was that since we cannot classify those graded algebras, let us do that in the language of conformal algebras. That's a different language of the circle operations. In other words, we bring a very strong restriction of polynomiality on structural constants. One can say, oh, it's a very strong restriction. Correct. But it captures all interesting examples. It's like, you know, algebraic curves is a very, very small subclass of all curves, but it captures all interesting examples. Okay, a conformal algebra is of finite type if, you know, once it is invariant with respect to derivations, every space which is invariant with respect to some linear transformation automatically becomes a module over the polynomial algebra. So this is a module over the polynomial algebra generated by that derivation, and we demand that that module be of finite type. It is basically equivalent to the, in the language of graded algebras, the dimensions of all homogeneous components are uniformly bounded. The multiplication of coefficients can be recovered from circle operations, so these are two equivalent languages. And classification of all simple Lie conformal superalgebras of finite type in this language was obtained by Katz, D'Andrea, Cheng, Fattori, group of people. The main idea was to basically to use this theory of linearly compact representations of linearly compact superalgebras of Cartan type. In the special and the representations in the last 20 years, the representations have also been classified. Initially, for all algebras except CK6, and for CK6 it was done only very recently, independently by Katz, Boya, and Liberati, and in our joint paper with Consuelo Martinez, which is still to appear. Well, this is the description of all irreducible conformal modules of finite type, say, over the Virasoro. All modules, Virasoro, if you remember Xanthelis Virasoro, it's algebra of derivations of Laurent polynomials. It acts on Laurent polynomials. So Laurent polynomials is the first module. And then it can be deformed by coefficients with beta, gamma. So this is a description of all of them. And they are not graded unless gamma is 0. Because you see, derivations, you decrease the power. And here you don't do it. Now, coming back to the original problem. If we don't want to speak this language of conformal algebras, if we don't want to impose polynomiality restriction, how can we classify at least all irreducible graded modules over the initial objects, over the all known superconformal algebras? If the conjecture is true, then over all superconformal algebras. Again, irreducible graded module means that, again, it is a sum of homogeneous components when you multiply degrees at, and all homogeneous components are finite dimensional. There are highest degree modules, lowest degree modules. It's where it is graded, but infinite only in one direction. And so Olivier Mathieu, in a different paper, classified all graded, irreducible graded modules over the Virasoro. He showed that there is a highest weight module or lowest weight modules. It's a different theories, very interesting theories. Or the so-called intermediate modules. I think they were first introduced by Fagin and Fuchs. Again, it's like Virasoro acting on Laurent polynomials, but deformed. In order to make them graded, we had to divide by this t. The proof is very delicate, very clever. You know, it's how with very clever proofs and very delicate proofs, it doesn't survive deformations. If we wanted to, we did not see how to generalize it to all superconformal algebras, for example. Now, well, the main result of this talk, again, Ron Graham already said that every talk should contain at least one new result. So this is a new result of this talk. Classification of all graded irreducible modules over all known superconformal algebras except these two small ones, including Navier-Schwarz. We are working on it, but so far they resist the method. Because the method is following. I don't want to go into these technical details, but I will mention this main idea. We arrange elements of these superalgebras, well, that has been done, and elements of the modules in formal distributions and check locality. So we prove that in some sense all structural constants are automatically polynomial. And then we use the known theory of representations of conformal algebras. To the best of my knowledge, this is the only case where these conformal algebras were used in the proofs. if you don't want to read the proof, you may not know what are conformal algebras. Well, these are technical details of how the proof goes, because basically you have to take modules over these conformal algebras and again change the derivation a little bit. Because if you just do that, you will get modules, but they won't be of finite type. You have to deform them a little bit, then they will become of finite type. And then you can do it. So theorem, all graded irreducible modules over superconformal algebras, except unfortunately these two, are just coefficient modules over from some known families. I think that in principle, the same approach may lead to classification of the superconformal algebras in the initial formulation. In order to prove that the existing examples exhaust all superconformal algebras, we need to put all elements in a nice way and check locality and use the known theory. That's it. Thank you.
And it's a very easy question, but I have my doubts. Do you like or you don't like superconformal algebras? These conformal algebras you are using, because sometimes you say that.
It reminds me, the question was whether I like superconformal algebras. It reminds me an old joke. Do you like tomatoes? I like to eat them, otherwise no. Well, I like them.
Yes, please.
So, as a conclusion, that your theorem gives some list of Lie superalgebras classification, right?
Modules over them.
Irreducible modules.
Yes, they're parameterized by highest weights, some integer parameters, some scalars from the field with certain conditions on parameters. But, well, this has been kind of known, that emerged in the last 20 years.
Can be written in by using structural constants, each representatives?
No, we didn't use structural constants directly.
Thank you.
Any more?